Evgeny Epifanovsky, and I'm a staff scientist at Q-Chem. It's a great pleasure for me to introduce Dr. Roberto Pivirati today, our speaker. Roberto received his PhD from the University of Zurich in 2010, and after that he joined Professor Don Truhlar's group at University of Minnesota. And in 2012, Roberto joined Professor Martin Head-Gordon's group at University of California, Berkeley, where he's spending time right now. And before I give the microphone to Roberto, I would like to remind you that we will be accepting questions from the audience throughout the talk. And please post your questions anytime. And after Roberto is done, we will go over these questions one by one. So please do not wait until the end of the talk and post your questions as soon as you have them. Thank you. Now, Roberto.
Okay. Thank you, Evgeny. Thank you, Q-Chem and the Q-Chem headquarters. It's a big pleasure for me to be here and give this webinar. As Evgeny said, I was raised and born in Italy. And so here's a slide about myself. So I was raised and born in the city of Genova, and where I got my Italian graduation. And then moved to Switzerland, working with Professor Kim Baldridge at the University of Zurich, where I got my PhD in 2010. And then later I moved to the US and work in the group of Professor Don Truhlar at the University of Minnesota. And fairly recently, I moved to the group of Professor Head-Gordon here at the University of California, Berkeley. However, today I'm going to present the results of my work at the University of Minnesota in the group of Professor Don Truhlar. So, as you can see in this slide, the talk of today will be about Minnesota functionals. So, it will be about density functional theory, which is one of the most used method for electronic structure calculation. And I'm going to present you the most recent Minnesota functionals, and also try to give you suggestions on how to use them and what are the best situation where you can use our functionals. So in order to do that, I have to have a few slides on a density functional theory. However, I will not go into the details of the theory at all, just very few slides to introduce what the exchange correlation functional is and how do we use it and what the Minnesota functionals are. So briefly, density functional theory is a very used theory, very useful theory, and it's based on the fact that it writes the energy of a chemical system in terms of the density. So as a functional, which is simply a function of the density. So the most used and widely applied implementation of density functional theory is called Kohn Sham DFT, well, at least in chemistry. And it basically brings back the orbitals into the description of density functional theory, but only as an auxiliary quantity. To calculate the kinetic energy of the systems. So as you can see in my slide, the expression of the energy as a functional of the density is in density functional theory is very simple, and you might be already familiar with this expression because it's an expression that is very similar to what the self-consistent field solution of the Hartree-Fock equations are, with only one notable exception, which is written here in red, and it's the exchange correlation functional. So that's an energy term, so it's a functional in density functional theory, and it basically groups all the unknown quantity in Kohn Sham DFT, and that's the only part that we need to approximate in a DFT calculation. However, the exchange correlation functional is very complicated, and it's up to right now, it's unknown. It's an extremely complicated function. It's highly non-local, and we need different approximation to be able to do a DFT calculations. So the most used application, the most used approximation to the exchange correlation functional are local approximations. So we use these simple scheme that I highlight here in this slide, which basically means that we approximate our functional as a local functional and integrate over all space. So as I said, this is an approximation, and is not even a very good approximation because, for example, we cannot get the correct asymptotic behavior of the exchange correlation, of the real exchange correlation functional, and of the real exchange correlation potential, which is simply the derivative of the functional with respect to the density. So since this is not a good approximation, many people suggested to go beyond the local density approximation, and they introduced what they're called the quasi-local or semi-local, although in a mathematical sense those are still local approximation, because we are doing one integral over the entire space, just one integral. But the quantity that we integrate depends not only on the density at every single point, but it depends also on some other quantities, such as the first derivative, the second derivative of the density, and so on. So we are including more non-locality in some sense into the description of our exchange correlation functional. So this idea was a big breakthrough in the DFT community, and it's the basic of this picture that you might already have seen. It's a very famous picture brought by Professor Perdue, which he called Jacob's ladder of density functional approximation, which means that basically you start from the ground, from a completely local approximation, and you climb the ladder, and at each step you insert levels of non-locality. You insert you pretty much make your functional better, hoping to reach the top of the ladder, reach the universal functional. So I will go briefly into these steps. So as I said, the first step at the ground is the local density approximation, where your integrand depends just on the density at the local point. And as I said, it's not very good for chemistry, although it's still pretty much used for solid state physics, for example. The next step, where your integrand depends on both the density and the first derivative of the density, the gradient of the density, it's called the generalized gradient approximation. And it was a big breakthrough for chemistry because this allowed DFT to be applied to chemical system with reasonable accuracy. We can go one step further and include terms different than the density and the first derivative. In this case, and which is the usual case, we include what is called the kinetic energy density, which is obtained from the Kohn Sham orbitals using this formula that I write here. The kinetic energy density is just a trick because it carries basically the same information that the second derivative, the Hessian of the density, has, but is much more stable in terms of numerical stability. So in some sense, we can say that this is a trick to use to include the information from the second derivatives into the functional description. Functional of this kind are called meta-GGA, and they are extremely important for this talk today because the Minnesota functionals are all meta-GGA. We're going to see that later. I have to make one more step, though, in the Jacob's ladder from Purdue, and go to the fourth step, which is the functional that include exact exchange. So these functions are usually in the chemistry community called hybrid functionals. So the exact exchange is sometimes called the Hartree-Fock exchange. Probably none of the two notation is exactly correct. However, I prefer the Hartree-Fock or Hartree-Fock-like notation. So as I write here, the expression of our exchange correlation functional is made up of two terms, basically. One that is the Hartree-Fock exchange. It's a scaled Hartree-Fock exchange, which is exactly the same as the Hartree-Fock exchange that we use in wave function theory, with the only difference that we are using Kohn Sham orbitals instead of Hartree-Fock orbitals. And we mix this term, which is completely non-local. So in this approximation is the first approximation where we include non-locality, real non-locality in the exchange correlation functional. So we mix this term with a simple local DFT term that can be divided in exchange and correlation, as I write here. So hybrid functionals are extremely important in chemistry. I think everybody knows B3-lip, which is probably the most famous functional in DFT in chemistry and one of the most used, and it's a hybrid functional. So let me jump now into the work that I've done in Minnesota. And before I introduce the Minnesota functional, let me talk briefly about the Minnesota databases. As you might know, the Minnesota functionals are semi-empirically optimized. They contain parameters that are fitted to experiment or high-level calculated data. And in order to do so, we need very good databases, not only to optimize our functional, but also to test the results that are coming from our functional. We need a collection of good databases to be able to understand how our functional really perform. So we recently collected all the databases from Minnesota in just one big place, which there's a website that you see here. You can go there. They are publicly available. You can use them, download them. And so, as I said, this is a huge collection of different databases, which is summarized by this slide. It's basically composed by 4 different groups. One is the chemistry energetic in the upper left corner. Then we have a chemistry structural, physics energetics, and the physics structural. The one that is most interesting and most important for today's talk is the chemistry energetic. It's our largest database, and is really we think it's the most interesting for chemistry and for chemists in general. So today I'm going to talk mostly of this database here. So how is it done? So what are these names? What are these acronyms stands for? So these are subsets of the main chemistry energetic database. The name, I know, I'm sorry, there's a lot of acronyms in these slides, but this is the summarization of the names of all the subsets. I'll try to go briefly and explain you and point you to the most important databases for chemists, for chemical interest. So, for example, the first one, the MGAE 109-11, main group atomization energies, as it says here, it's very interesting for chemistry. It's one of the largest database that we have. Also, going down, you can see all the other databases. Two other databases that are particularly of interest and particularly important for us are, for example, the HTBH38 and one below it, and HTBH. Those are the transfer barrier heights, hydrogen transfer barrier heights and non-hydrogen transfer barrier heights. So this gives it gives you an idea on the performance of a method for the chemistry, the kinetics of the chemical kinetics. Another important database is the one below, the non-covalent complexation energy, especially for DFT. You all know that DFT is problematic for non-covalent complexes or van der Waals complexes or dispersion-like complexes. So this is a database that you should keep an eye on if you're interested in non-covalent interaction. Okay. So with these databases, I'm going to present you some results on the Minnesota functionals. First, though, I have to introduce the Minnesota functionals. So what are the Minnesota functionals? Well, they are they're different families of meta-GGA or hybrid meta-GGA functional exchange correlation functionals. So you'll see here a few names starting from MO5, MO6, MO8, M11, and MN12. I will not talk today of the MN12 functionals, which are oriented more to solid-state physics and chemistry at the same time. I will talk of the first 4 generations, which are the one that are most important for chemistry, and they are the one implemented in Q-Chem. So, a little bit of history. The history of Minnesota functional started in 2005 with the first 2 functional, MO5 and MO5-2X. So if we plot these functional in this way, where on the left we have 0% Archifock exchange, and on the right we have 100% Archifock exchange, we can put the MO5 in this location. So you'll see. You'll see also in the next generation this trend. There's one functional that is pretty much in the region where around 25% of Archifock exchange, and another functional which is usually dubbed 2x, which is twice the number of the percentage of Archifock exchange of the first functional. So in this case, MO5 is 28% Archifock exchange, and MO5-2x has 56% of Archifock exchange. So there is a little bit of confusion why we did that, why my predecessor at Minnesota decided to do that. I hope to clarify it today. I hope to clarify today with this slide, where I represent the results in terms of mean unsigned errors for the databases that I've shown you before, for both functional MO5 and MO5-2X. So MO5 is blue, MO5-2X is red. It's pretty easy. And here on the left, I basically summarize the winner. So which one is better? So, and you'll see a trend here. So the trend is this one, that for most databases, especially for the one that are interesting for chemistry, as I said before, main group atomization energy here at the top, and here at the bottom, HDBH and HDBH, the non-covalent, so the barrier heights, the non-covalent. For all these databases, the best functional is MO5-2X, so the one that has a high percentage of Hartree-Fock exchange. However, if you go at the bottom line, the CE345 is just basically the mean unsigned error over all the 345 data, including all of the data in our database. You see that the best function is MO5. So really, this is a trend that is common also to the other Minnesota functionals. The one without dashes, so the one that is dubbed MO5, is really the best overall functional. So if you have no idea of what your system, of what the interactions in your systems are, and you have no idea of what your system look like, the best shot that you have is by using functionals such as MO5 or MO6, the one without dashes. However, if you know that your system, for example, it's mostly composed of regular organic chemist type interaction, then you have a well-behaved system. You know exactly what you are calculating. Then probably a functional that is more specialized, like MO5-2X or MO6-2X, is best for that particular system. On the other side, these two databases here, the SRMBE13 and the MRBE10, which are the two databases for which MO5 works best, are databases containing metals. So when you have metals, even if you have if you suspect to have multi-reference character or not, functional with high percentage of Hartree-Fock exchange are not gonna do well. So really, the best functional in this case will be the one with the lower percentage of Hartree-Fock exchange. Now, back to the first slide, the one where we introduced the Minnesota functional. The 2005 generation is considered almost obsolete because it was substituted in 2006 by the 2006 generation, which is composed by 4 functional, as you can see here. So it pretty much covered the entire spectrum of percentage of Hartree-Fock exchange, going from the 0% completely local functional, MO6L, that's what the L stands for, going to MO6, once again in the 25% range. In this case, is 26%, 27%. Then the MO6-2X, so twice the number, once again in the 50% range. So we are 54% here. And also there's a fourth functional, MO6HF, which has 100% artifact exchange. I'm going to talk about this slightly later in this talk. Also in 2008, there was an attempt to create a next generation called MO8. Those are two specialized functional, and I will present some results later. And they are basically on the same level as MO6-2X. So if I present again this slide where we compare the performance of the different MO6 functional now, which are very much interesting, you'll see a very similar trend to what happened before. So here there are only three functional, MO6L, MO6, and MO6-2X. MO6 is the red one, and as you can see by analyzing the total, is the best overall functional. So once again, if you have no idea, no clue of what your system will look like, of which kind of interaction are in your system, probably MO6 is the best shot that you have. However, if you know, for example, that you have a barrier height or an optimization energy, then MO6-2X, so the one which has a high percentage of artifact exchange, will definitely be better. MO6L is another specialized functional in some sense. It's local. It doesn't have artifact exchange, which is a good thing because it scales better. It scales one order of magnitude better than hybrid functionals. It's good. It's good pretty much only for metals in these two cases here. It's the best case only for the multi-reference bond energy, this database here. However, it's not that bad. So if your system is very large and you cannot afford to use a hybrid functional, for example, you have scaling concern, then MO6L is still a good functional. So I haven't talked about the three functional here. So as I said, MO8HX and MO8SO presented in 2008. They are, as you can see from the diagram, they are in the high exchange range. So they have around 50% artifact exchange. They were an attempt to change the functional form, a successful attempt to change the functional form towards using a better functional form. But the results, in terms of the results, if you are interested in what do they perform for calculation, they are pretty much on par, on the same level of MO6-2X. The other functional that I haven't presented is MO6HF. So this is a very specialized functional. The performances for all these databases are not as good as the other Minnesota functionals because it has 100% artifact exchange, but it's particularly important and it's particularly good for problems where the self-interaction error is crucial in DFT. For example, the classic example is calculation of a charge transfer excited states with TD-DFT. So this is basically the situation when I arrived in Minnesota in 2010, and we were interested to make new density functional in the Minnesota group. So I was facing basically three big challenges that I've summarized here. One is that you need basically a specialized functional to improve to have a good performance for excited states calculation. The second, of course, it should be good if we can improve the reliability of MO6L, the local functional, for example, for chemistry, and also try to reduce the number of functional, because 4 functionals in one family is kind of a big number, and people sometimes have confusion on which functional to use. So let's first tackle the first point, performance for excited states calculation. So here are some more data on this problem. So this is a very simple database, which is not included in the Minnesota database that I showed you before. And it's a database that is composed by medium range charge transfer excitation energies that are usually calculated with TD-DFT. three very simple systems. So the results with conventional DFT, Minnesota functional MO6L, MO6, even the MO8 HX and SO that I mentioned before, are pretty bad. You see that no functional is better than 2EV, which is a very, very unexpected result. We're not happy about that. The only functional that solved this problem at that time was MO6HF, the one that has 100% RTFOC exchange. So in 2011, we presented this functional called M11, which basically make use of a new concept in the DFT community introduced by Savin in the early 2000, if I remember correctly. So the concept of range separation, it's a very simple idea. In hybrid functional, regular hybrid functional, we have this kind of situation that you see on the screen. So the percentage of RTFOC exchange and the percent of the DFT exchange is constant. If we plot it against R12, the interelectronic distance, the percentage is constant. However, what we can do is separating the interaction, the interelectronic interaction, and basically make the percentage of RTFOC exchange varies from some number in the short range limit up to 100% in the long range limit, and the DFT exchange ranging complementary from some number in the short range to 0 in the long range. So in the very long range, you pretty much have a functional that has 100% RTFOC exchange. And this cures the self-interaction and the self-interaction error of DFT in the long range, which is basically the most important, the error that is responsible for the bad behavior with TD-DFT calculations. So as you can see in this slide, which is the same slide as before with two extra functionals, two extra results, the functional that have range separation really cured this problem. So M11, that is the new functional that we presented, that use range separation, has an MUE below 1 EV, so we were quite happy about this result. Also, I include here the omega B97X functional, which is a very important functional from Ed Gordon's group, and this functional also cured this problem. Here's another example on TD-DFT excitation energy calculation. So these are three databases containing valence excited states, Rydberg excited states, and charge transfer excited states. So these are the black, the gray, and the blue one. The meaning of this picture is basically if you have a bar in the red region, it means that your functional is worse than average. It's no good. What you want is bars in the green regions. So if a functional has 3 bars in the green region, well, that would be the perfect thing. And the only functional that are good here, as you can see, are probably the one that has a very high percentage of RTFOC exchange, MO62X and MO52X. These are the functional regular hybrid. If I add here the range separated hybrid, then you'll see that all range separated hybrid have all 3 bars in the green region. So these are very good for all 3 of these type of interactions of excited states calculation with TD-DFT. This is even better than before, because as you can see, the MO6HF result, MO6HF was pretty good for Rydberg charge transfer excited state, but it was not very good for valence excited state. While range separation, including M11, which is our new functional, are really good for all 3 types of excited states. So how does this functional perform for the databases that I've shown you before, the regular one in the Minnesota databases? So here's again the databases, the subsets that I was talking before. I will not include the multi-reference bond energies here because these are high exchange functional, so we don't expect them to be good for multi-reference. They will be all pretty bad. So both the multi-reference and the atomic energies will not be included in the next slides. But here are the results. So if we compare M11 and M06 to X, then you'll see that pretty much over all the subsets, the results are very, very similar. Even the overall one, the CE3180, 18 right now, are very similar. M11 is only slightly better, but not significantly better, not statistically better than M06-X. So this was a good thing. We've achieved M06-X performance and also fixed the excited states, the TD-DFT excited states problem with just one functional. If we compare M11 to other hybrid functional, other popular hybrid functional, then the results of our functionals is immediately put in perspective. So this is a comparison with B3-lib, one of the most popular functional, and B97-3, one of the best hybrid GGA on the market. And you'll see here that the performance of M11 are extremely better than B3-lib and B97-3. The overall, in terms of the overall quantity down here, we are more than 50% better than B3-lib. And for each databases, for each subset, we are usually much better than B3-lib. Okay, so this brings me to the second point of my story that I was mentioning before, improving the reliability of local functionals, if it was possible to do that. Of course, let me present you an example like I did before. So this is an example where local functionals are not really very good. So chemical kinetics, so barrier heights, as I was mentioning before, the barrier heights databases, these are the results for one of the barrier heights databases, the HTBH38. Hydrogen transfer barrier heights, 38 reaction. If we compare regular local functional and regular hybrid functional, we immediately see that the performance of hybrid functional is much better. So if we compare, for example, B-lib to B3-lib, which is a hybrid functional based on B-lib, there's an increased performance. The performance of B3-lib is way better than B-lib. Same thing is for PBE versus PBE0. Same thing is for SOGA 11 versus SOGA 11X. These are other functions that we developed in Minnesota group. These are GGA. All of these are at the GGA level. But even at the meta GGA, MO6L and MO6-X are way different. MO6-X is way better than MO6L. So if we can improve the performance of local functional for regular chemistry, we would be, and specifically for kinetics, we would be very, very happy, because local functionals are much more affordable. They scale better than hybrid functionals, so it will be a good thing. So this brought us to the development of what we call the M11L, where L stands for local, as MO6L, so successor to MO6L. So how did we try to improve on local functionals? So M11 was a big innovation compared to MO6-X by adding the range separation, as I showed you before. You see this picture before. But how can you do that at the local level? You don't have a Hartree-Fock exchange, and we don't want Hartree-Fock exchange. So what can we do? One of the idea that we tried, the one that was successful, is basically to still use a sort of a range separation. And in this case, we call it dual range, because we use one meta GGA, one DFT meta GGA functional form to describe the short range, and one meta GGA functional form different than the first one to describe the long range. So this allowed us to have very good performance with just a local functional. As you can see here, the slide that I showed you before, if we compare the MO6L to MO6-X and M11L, see that the performance of M11L for these databases are much better than MO6L and on par with MO6-X with no Hartree-Fock exchange. So we're quite happy. So how does it perform for all the other databases that I've showed you before? So all the previous subsets. So here's the comparison. MO6L versus M11L. So both are local. but as you can see, M11L is pretty much everywhere better than M06L, especially for the overall. It's a sensible improvement here. It's not only a minimal improvement. This is a true, real improvement. It's even more interesting when we compare to other local functional. For example, PBE is probably the most used local functional. It's a GGA, and the performance of PBE of M11L compared to PBE are quite better, as you can see from this slide. The overall, we improved by more than 50%, and even for those subsets that are interesting for chemistry, as you can see here, the atomization energy is hugely improved. The barrier heights are hugely improved. PBE is basically not usable for barrier heights. Even non-covalent interaction are much better. So pretty much overall, a very good improvement. Okay, so this pretty much brings me to the third point, which explains itself. I mean, it's a consequence of the first 2 points. In fact, that we now have two functional, M11L and M11, which are both great for the databases that I presented you before. So we don't really need more functionals in a family. So here's, for example, a comparison between M06, M06L, and the M11L. So you see that M11L, so those are the same databases that I showed you before. I've only added M06 down here in this yellow-orange color. So you see that M11L in the overall and pretty much in all databases is probably more similar to M06 than to M11L, to M06 than to M06L. So in some sense, the picture of the Minnesota functional is now composed in 2011 was composed by just two functional. So this is the final picture. So we now have one generation with two functional. One is a local functional, no Hartree-Fock exchange at all, and the other one is range separated. So there's this arrow down here because it covers the entire, well, this spectrum of Hartree-Fock exchange. So these two functionals simply substitute the whole four functional in the previous generation. Once again, the one with the dash is a specialized functional. It's local, so it's probably good if you want good scaling, if you have a big system. And the one without dashes, just M11, plain and simple, is probably your best shot if you have a chemical system that you don't know, and you don't know what kind of interaction you have, and this is your best shot when you have to choose a functional. Of course, if you have multi-reference or metals or something that is not very happy with the high percentage with Hartree-Fock exchange, then you are going to use M11L because that's the only thing that you can pretty much do. Okay, I'm approaching the end of this webinar. I want to give a few suggestions on how to practically use this functional in Q-Chem. So all these functional M05, M06, M08, and M11 are available in Q-Chem starting from version 4.0. Previous version, I think still M05 and M06 were available in the Q-Chem, in the previous version of Q-Chem. Thanks to Yihan, I think you'll be able also to do TD DFT starting from Q-Chem 4.1. The keywords are pretty simple. It's just in the RAM variables exchange and then the name of your functional, like M11L or M06L or M11, whatever. No dashes. You don't need to specify the correlation, even if it's an exchange correlation functional. The keyword for Q-Chem is just exchange M11L. A practical suggestion is always to use a fine integration grid when you use any meta GGA functional. We've tested this functional for grid sensitivity. We've improved the functional form, and the functional form is much less sensitive to the grid size than the M06, for example, functional form. But still, we suggest you to use at least a 99-590 integration grid. Meta GGA are very provide a very fine description of the integrand. So if you use a grade that is not sufficient, you're going to have trouble anyway. So this type of grade is the one that we always suggest. At least you can obviously go higher with the radial number of points if you need. And optimal results, as I write them here, are usually obtained with triple zeta basis set. Don't forget that these are semi-empirically optimized functional, and they've been optimized with triple zeta basis sets. So I write here a keyword basis CCPVTZ. You can, of course, use any kind of a triple zeta basis set. You don't have to use CCPVTZ. CCPVTZ is probably even too large for the DFT calculation. But of course, you always have to be sure to be converged in terms of the basis set that you're using. And usually, this is a common theme, we suggest to not correct for BSSE using counterpoise because it will introduce other problems in the description in the results. So these functions were not optimized to use counterpoise correction. We suggest to not use it. Down here, as I said, these functions are pretty popular. They are implemented in any quantum chemistry software. If you're interested in solid states, maybe LibXC and BASP are very much used, and then obviously the other software for chemistry that you might might have already seen. Finally, if you need more information, there's a Wikipedia page on Minnesota functionals. So you can search Minnesota functional on Wikipedia. If you're interested, there are a few other suggestions on how to use them and which functional is better for which. And also, I suggest you to look up this article, which is a review article that we've just submitted. It was just accepted. It will be published in the Field Trans Royal Society A as a part of this theme issue for the DFT for Physics, Chemistry, and Biology. The preprint is already available on the archive website. All the results that I presented today and much more, all the numbers and the results for each subset, all the databases, and a very thorough explanation of all the databases, all the basis set that we used, all the results for our functional and for the other functionals that we consider are in these articles. So it's a monster article, are either there or in the supporting information. So I suggest you, if you want to go and check out this article. Okay, so that's pretty much it. Let me finish with some acknowledgements. Of course, my thanks to Professor Don Truhlar and the entire Truhlar group at the University of Minnesota, and obviously Professor Heath Gordon here at the University of California, Berkeley. Financial support down here, Swiss National Science Foundation and the US funds, and obviously the biggest thank is to Q-Chem and Ian, Jengting, Emil, and all the people at the Q-Chem headquarters for inviting me to give this webinar, give this talk, and thank you for your attention. That's it. I give the talk back to Evgeny, and we are now accepting questions.
Yes, thank you, Roberto. It was a great talk. Now, request to the audience, if you have a question, please don't hesitate and send it through the questions box. And now we are ready to take a few questions. Well, the first question is, which functional from the Minnesota family is the best for the description of non-covalent interactions?
Yes. Okay. So this is an interesting question. As I think I've already showed in the talk before, that Minnesota functional are pretty good for non-covalent interaction, which somehow surprises people because we don't have any semi-empirical dispersion or molecular mechanic dispersion terms like the DFT-D or any other non-local functional or anything. So how can we get good non-covalent interaction? Well, the real reason is that most of the non-covalent interaction that we are interested in chemistry are not really long-range R⁻⁶ interaction. They are more like a medium-range correlation. and in this range, the vast majority of non-covalent interaction in chemistry can be described by a meta-GGA functional like the one that we have, which is parameterized to catch the middle range correlation. Obviously, there's no hope that we can get the R to the minus 6 tail or the R to the minus 6 behavior with Minnesota functionals. But with the middle range regime is there. And this allows pretty much all Minnesota functional to be good for non-covalent interaction. So in order to answer more specifically the question, I think that the functional I've shown you before, the functional with a high percentage of RT-FOC exchange are particularly good for non-covalent interaction. So you either have the choice of M11 or MO62X is probably more tested because it's out there since quite a longer time. But I think M11 would be as good as MO62X.
Thank you. Sorry. The next question is which functional from the M11 family would be better for the transitional metal complexes and multi-reference systems, and how do those functionals compare to, say, B3P86?
Yes, so B3P86 is a pretty popular functional in the community of people that are doing calculation on transition metals. So we do have the results of B3P86 in our archive paper. So if you want more exact number, you can check it out on that paper. But in general, our local functionals are much better than B3P86, the newest one in particular. M11L is much better than B3P86. Even MO6L is better than B3P86. So those are really huge improvement over this functional. I have to say though that probably multi-referenceness is one of the biggest challenge of DFT for the future. It's not a solved problem. The multi-reference database that we have is probably a little small, and really the performance that we have with the Minnesota functional, with any functional, not only Minnesota functional, with any functional in DFT are not satisfactory, are not on the same level as for atomization energies, for example. So really, I think that multi-referenceness stands correct with the name. It's really one key improvement that the newest DFT should tackle. But right now, the best choice, I think, are M11L and MO6L. And in any case, I still think that a local functional would be better than a hybrid functional like B3P86 is.
All right, thank you. Our next question is, again, a request for a suggestion which functional would be the best for treating two non-covalent interactions. Two particular cases of non-covalent interactions, like hydrogen bonding and halogen bonding.
Yeah, I think this goes really fits perfectly with the question the answer that I gave before. So the high exchange functional are probably very good for non-covalent and hydrogen bond as well. So you can pick M11 or MO62X or MO8HX. The only reason not to use these functional that I see is that you either have a metal in your system or you suspect that your system has somehow a multi-reference character. So in this case, then high percentage of RT-FOC exchange will not be good. But in all other cases, if you have hydrogen bonding or dispersion-like interaction, the high exchange functional are probably the best way to go.
All right, and then let's take our last question. So it's a very particular question. If we go back to the slide where M11L is compared with M11, let's go back to that slide.
Yeah, I think it's either this one or this one here. Or maybe you mean the range separation slide, this one.
So the question is about comparing comparing the database results on the M11L. Let's see which slide that is.
It might be the DFT. This one maybe.
Okay, well, I guess the question is whether M11L has range separation in it.
Well,
But
yeah.
It's a local functional.
Yeah, M11L doesn't have range separation in the sense that doesn't have Hartree-Fock exchange. So we're not exactly sure if your question, if you want to elaborate a little bit more, we'll be happy to try to explain that. But if you are referring to TD-DFT, M11L is a local functional, doesn't have Hartree-Fock exchange, so it still has self-interaction errors, which means that basically we will not be extremely good for TD-DFT. So if you want to do charge transfer or even valence and Rydberg excited states with TD-DFT, we suggest you to use always a functional with Hartree-Fock exchange, and the range separated functional will be the best in this case. So M11 with no dash L, just M11, plain M11, or you can still use omega B and A7X. Of course, those are good functional if this is the slide that you are referring to.
Okay. It appears that we have a couple more questions.
Yeah.
Okay. In the end of your talk, you mentioned that using BSSC for correcting using the correction for the basis set superposition error is not recommended with the Minnesota functional. Yeah. Could you comment on that? Why that causes problems?
Yes. The short answer is that we didn't include any counterpoise correction when we were optimizing the parameters for the functional, and therefore using counterpoise correction when you're trying to do a calculation brings back some errors in our functional and simply give you a nonsense result in some cases. So I still believe that the best way to do that is not to include counterpoise corrections because we know that a counterpoise correction is not a perfect method. It doesn't exactly solve the basis set superposition error problem, and we believe that we already solved it by using a parameterization with triple zeta basis set. So it will simply there's the risk that it will give you wrong result and strange results. So in all our calculation, we never do that, and we have pretty good performance for systems that are completely different from the one that we trained on. So we're reasonably sure that you can use it without counterpoise correction.
All right, thank you. Okay, and so our last question is, what's your recommendation on the functional to use for description of pi stacking interactions and XMRs and things like that?
Well, yes, this falls back exactly on the same page as the non-covalent interaction. So if you can use M11 or MO62X or MO8HX, those are the best choice. I understand if you have to, if your system is large and is getting larger and larger, you might not afford a high exchange functional, a hybrid functional at all. So you might be stuck to MO6L and M11L, which though are not bad at all for non-covalent interaction. You have an idea here. So you see that non-covalent interaction, even with local functionals, are sorry, that's not the right one. So here we are. So non-covalent interaction, even with local functional, are pretty much covered. The mean unsigned error for our database is below 1 kcal per mole. And in all other tests that we've performed, like S22, S66, the mean unsigned error is on the 1 kcal per mole range. So if you can afford a high exchange functional for your system, that will be optimal. If you can't, and if you want a faster calculation, even M06L or M11L will be pretty good for pi-pi interaction or non-covalent type interaction.
All right, let me thank Roberto again for giving this talk. And I think that brings us to the end of this webinar.
This concludes our webinar. We would like to thank Roberto Pivirati for his excellent presentation. If you've not tried Q-Chem lately, we have come a long way, and we invite you to utilize our 2-month full-featured demo, which you can request by hitting the orange free demo button on our website. Should you have any questions, please feel free to contact us by emailing either Jinting or Yihan at the email addresses noted on your screen. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.